So, we were looking at two-dimensional finite element analysis in the previous class. Since it has been some time, we discussed this. The mid-semester week was in between. So, I will just take you over whatever we discussed. We were thinking of transitioning from one-dimensional finite element analysis to two-dimensional analysis. So, we discussed how a problem becomes 2D or even 1D or 3D or 4D if we bring in time. And then we identified some key challenges in going simply from one dimension to two dimension. The first challenge that we identified was that I have to now model a geometry in two dimensions. This geometry would include some curves, chamfers, fillet radii, holes, curved shapes in general, aerofoil shape of a wing, for example, or a fuselage body, like this. So, we realized that if we have straight edged elements, triangles, quadrilaterals, to model a curved geometry would be difficult. We could probably be actually adding material where it was not there in the original system. We might be missing out some material where it was already there. We would be putting a hole. So, we called this as a discretization error. I am actually adding volume or probably missing out some volume in the total geometry of the system itself. That is the first challenge we faced. The second challenge we faced is that when we tried to derive the shape functions, it became a very laborious process. And a point that I highlighted was that when you looked for one-dimensional problem from linear to quadratic, we tried to go for all the terms in the quadratic, that is constant, linear and quadratic, complete polynomial. Here if you try to do that, you might miss out some terms, you might have extra terms. Okay. That is also possible, we realized, in that triangle of arrangement of binomial coefficients, etc. Another important challenge we had was that if you look at two-dimensional elements, suppose two rectangular elements, when they join, irrespective of the number of nodes on this edge, when they join, across all these points on the interface, whether that point belongs to this element or this element, the field variable has to be the same. Let it be temperature or displacement or velocity or electromagnetic potential, whatever, that field variable, it has to be the same. And there are an infinite number of points on this edge. In one-dimensional problems, it was just entire cross section anyway is the same as per our assumption. So, therefore, when two elements joined, it was just one point, and that point had the same temperature or velocity or whatever, either belonging to this element or this element, and so therefore, continuity of the field variable was not an issue at all, because that was the variable taken at the nodal point itself. So, it was always continuous between elements. But now, we faced a new challenge that it is not one point, but it is a whole edge. So, it is not enough if I make sure that the temperature is same here and here at the two nodes on the edge. But for all the points in between also, I have to make sure temperatures are free, whatever is the field variable, it is the same whether I come from this side or this side. Making sure that the first derivative is continuous is next level of challenge. But first, field variable itself should be continuous. Our gold standard is the exact solution. Exact solution will be continuous, not only field variable, first derivative, second derivative, third derivative, whatever exists will all be, that is our gold standard. But first, I am thinking of at least let f of x, y be continuous whether it belongs to this element or this element. That's the next challenge we identify. Of course, I pass all these challenges, I actually plug in to the system either weighted residual formulation or the variational formulation in minimization of a or stationarity of a functional expression. I have to evaluate now double integrals. Double integrals over curved domains is going to be a pain point for us. So, these are some of the challenges we identified, and we said for all of these challenges, the magic wand solution is natural coordinates. I would define a new system of coordinates in which I will do all the computations. They would not be xy. Xy is the real physical coordinate system, xy or whatever coordinates that you choose is the real physical world, but I would choose some coordinate system zeta eta in the mathematical world which would simplify and solve all these challenges that we noted. How does it do that? We proposed that in those natural coordinates, for say quadrilateral elements, I have taken first, I have posed it as zeta eta coordinates. The parent element will be a perfect square. The coordinates zeta and eta vary from -1 to +1 always. Okay. So, it is a 2 by 2 perfect square in the natural coordinates, the element always, irrespective of whichever problem you are solving, irrespective of whatever is the actual domain in the real physical xy coordinates. This is the element over which I will do all my computations. This remains behind the computer screen. You won't see this element. It is only in the maths, in the calculations. In the real physical world, that element could still be x1, y1, x2, y2, x3, y3, x4, y4. So, it is a general quadrilateral element. So, what I am proposing is that let there be a coordinate transformation first from xy to zeta eta frame. All that I am interested in is in this real physical world, I agree. Okay. Field variables variation over the real physical world. Its derivatives with respect to x and y, first derivative, second derivative, whatever is of interest to me is with respect to x and y, I agree. But computations I want to do in this zeta eta frame. So, this would mean a coordinate transformation. When I do a coordinate transformation, I am saying that for every point in the real physical world, there is a corresponding point in this 2 by 2 square. So, you could flip this argument and say that this 2 by 2 perfect square element, I am actually distorting it, stretching, rotating, whatever you want, okay, into this quadrilateral. But as long as I use linear distortions, transformations, a straight edge can only become another straight edge. So, 1, 2, 3, 4 perfect square will be 1, 2, 3, 4 quadrilateral, thus that is all that it can be, okay. But still it is a tool for me to handle general quadrilateral elements in the real physical world. I have to think of how I would model curved elements, etc. Later on we will see that, but right now at least it seems to be promising approach. We will work out the details and then we will see how it works. So, now we have two levels. One is that I have to model xy to zeta eta, coordinates itself I am doing a transformation, and then I am doing the field variables modeling. So, coordinate modeling, geometry modeling, and then field variable modeling. There are two aspects to the finite element modeling when we come to 2 dimensions, 3 dimensions. This complication or an extra twist to the story is not really required in 1-dimensional cases, because all of us are fairly comfortable doing d by dx, d square by dx squared or integral dx, etc. You are very, very familiar So I have not introduced these natural coordinates in the one-dimensional case. Some books do introduce natural coordinates from the beginning itself. But since it is not necessary, I didn't want any distractions, complications. To understand the basic concept formulation, you don't need natural coordinates, so I didn't want to introduce that. But now you require it, so we bring it in and try to figure out the coordinate systems and so on. So what we are doing from geometry modeling is that a perfect square is there and it is distorted or transformed to a general quadrilateral. Any point P in the real physical world will have a corresponding point P prime in the zeta eta coordinate. Any point Q prime in the zeta eta frame, that perfect square, will have a point Q in the real physical world. So first we need to figure that out, then on top of that we will figure out the field variables mapping. Is that okay approach? Any doubts, please feel free to ask me. So this is what I am going to propose. Since we are familiar now with shape functions, interpolation functions and so on and so forth, I am going to say x and y coordinates themselves. First I concede that node 1 here, whose coordinate is -1, -1, is mapped to x1, y1. Node 2 is mapped to x2, y2. Node 3 is x3, y3. Node 4 is x4, y4. 4 nodes का हो गया. Okay, mapping from zeta eta coordinate where its coordinates are always fixed, -1, -1, -1, 1, 1, 1, 1, -1, 1. Okay. So those coordinates are fixed. In the real physical world, let them be any coordinates x1, y1, x2, y2, x3, y3. So I will do this interpolation mapping through some shape functions for the coordinates x. If I do for coordinate x, I can use the same shape functions for y also, because x or y, how does it matter? It is only linear transformation. In fact, I would propose that I would use the same shape functions instead of x or y. If I call it T as temperature, it could be the field variable. Displacement u, it could be the field variable. So same shape functions I can use for geometry modeling as well as the field variable. Let me see how I will find out. How did we find out in the earlier case? Same thing that mid-semester paper also you have solved one question. So the same thing here. Linear element, 4 nodes. So I can take 4 terms in f of zeta eta now. So C0, C1, C2, C3. I have taken 4 terms. When I substitute nodal coordinates node 1, -1, -1, then I should get x is equal to x1. Okay. So I substitute it. I get 4 equations when I substituted the 4 nodes. So I solve for C0, C1, C2, C3. I substitute them back again and then rearrange the terms. So that would give me x in terms of x1, x2, x3, x4. For any point in between, within the element x, I will get this. Is that okay? But if this is the process we wanted to do, then what is the big deal about natural coordinates? So I don't want to really do this. It can be done like this. That's what I want you to understand. So I can get the shape functions like this. Once I have got it for x, I can use the same shape functions for y, for field variable u or t or whatever it is. Okay. These are linear in terms of zeta and eta coordinates. Fine. Is the process clear? Just as we just now discussed for the question 2 of mid semester. Okay. Process is straightforward. Only doing it is laborious because you are dealing with 4 equations in 4 unknowns, C0, C1, C2, C3, उसको उल्टा करने का है, then rearrange करना है. It's a laborious process. So, okay. So what I propose, because I said Natural coordinates is an advantage. It will not give you this nuisance of laborious way of finding shape functions. That was our challenge number 2, I think. Yeah, process of finding shape functions, tedious derivation. But then when I introduce natural coordinates, what I am doing is the same process. So, that is laborious anyway. So, I have to give you some shortcut way of doing it. While this can be still done, okay. So, let us take a minute before plunging into again answering the question, paper hai, pen hai, solve karo. Before that, just keep the pen and paper aside, think about it. What are we trying to achieve? We are trying to get a x or y or temperature T or whatever it is, F. N1, F1, N2, F2, N3, F3, N4, F4. Now, whatever be N1, N2, N3, N4, if I substitute the coordinates of node point 1, okay, wherever I am, this formula will be valid within that element, wherever I am. But if it becomes node 1, I substitute the coordinates of node 1, F expression should reduce to what? F1, correct? That means N1 should become what? 1, N2 0, N3 0, N4 0. So, what is the nature of the shape function, interpolation function that I am trying to find? When I substitute that node coordinates, that shape function should become 1, all others should become 0. Okay? Please understand this carefully, because once you understand this, rest of the discussion is fairly straightforward. So, I am looking for a function which would take the value of 1 when I substitute that node ka coordinate, and should become 0 when I substitute any other node coordinates. At all other nodes, it should become 0. Same for all the shape functions. Now that we understand this is what is the function I am looking for, without doing all the tedious derivation, can I simply write it down? Because this is a perfect square of 2 by 2, minus 1, minus 1, 1, minus 1, 1, 1 and minus 1, 1 are the 4 coordinates, vertices. Edges are perfect straight lines. It is a perfect square, 2 by 2. What could be? For example, let us focus on N1. I want to get N1. Process to maine bataya, this whole process you can get it, okay. And what we got is 1 minus zeta into 1 minus eta by 4, okay. I want you to get that expression directly without doing this process, because then I can use it for more complex elements if we are able to do it, okay. So, what is the process by which I can directly look at that element and write it down ki this should be the shape. N1, let us focus, or if you like N2, N3, N4, whichever, it's up to you. But what I am looking for is it should be 1 at that node and 0 at other nodes. So, I have written it down like this. What would be when we substitute coordinates of node 1, N1 should be equal to 1, N2 should be 0 and so on, and vice versa for all the nodes. So, how do I write it down? By just looking at it. How do I get a function f of x, one dimension de soch lo first, just f of x. When I substitute a coordinate, it should become 0 or 1, whatever. When is it 0? F of x, I substitute a value of x, 2, 3, 28, f of that should become 0. When will that happen? Huh? Pardon? So, when does it happen in general? Huh? Direct delta function, okay. Any f of x, it is the root of that function. Okay. Or if you think of it graphically, when will that happen? Huh? So it is a point on the line, then it would satisfy that equation. It becomes 0, right? So graphically, if you think of, if I am substituting a point's nodal coordinate, that function should become 0. Means what? It is a point on that line. Then it becomes 0. Now can you tell how I will write n1? Because n2 should be equal to 0, n3 should be equal to 0, n4 should be equal to 0, etc. n1 alone should have some value. That value I want it to be 1, we will see that part later on. n1 should not be 0. Okay. So now think in terms of graphically lines and equations of lines that would suit your purpose. Okay. Let us look at it this way. What is 0? n1 should be, whatever is a function that I would find, should be 0 at node 2 and node 3, correct? Whatever I will eventually find, it should be equal to 0 at node 2, node 3. I am looking at one edge, okay, then I will come to node 4. If it is 0 at node 2 and node 3 and it is linear function, 0 at entire edge. For all the points on 2 and 3 line, what is 0 for all the points on 2, 3 line? So, don't worry about the expression. In principle, what would be 0 for all the points on the edge 2, 3? What is the expression that would be satisfied by all the points on the edge 2, 3? Huh? Zeta equal to 1 means what? What is zeta equal to 1 in this case? Huh? What is that? What is zeta equal to 1? The equation of the line, right? So, equation of the line 2, 3 would be satisfied by all the points on the line 2, 3, not just node 2, node 3, but all the points, which is what we want, right? Okay. Now, think of how I can find n1, which would be 0 for 2 and 3 and 3 and 4. 4 also it should be 0. How would something be 0 for 3 and 4? Multiplied by? Points of the line 3, 4, correct? That is equation of the line 3, 4. So, if I think in terms of multiplying the equation of line 2, 3 and 3, 4, which in this case is actually very, very simple. Zeta is equal to 1 and eta is equal to 1. So, I just write 1 minus zeta, 1 minus eta, right? But when I substitute the coordinates of node 1, which is minus 1, minus 1, correct? How much it has become? 4. So, I want it to be 1. So, what I should do? आपको क्या मिला था? 1 minus zeta into 1 minus eta divided by 4. After doing all this, that is what you got, right? And next one you can easily guess now, what would be n2? 1 plus zeta into 1 minus zeta divided by 4. So, I am going to write it in general like this, some product of two lines multiplied by or divided by that scale factor, because it has now to become 1. Is the logic clear? So, I do not need to really go through the entire derivations, tedious process. I can do it by looking at the element, okay, because the shape function would be like this. It would be 1 at that node, centered at that node. What we have drawn here on the blackboard with the linear shape functions for one dimensional analysis, it is going from 1 to 0 at the other node. Here it would be 1 to 0 at the other two nodes also. Node 1, it is 1, 2, 3, 4, it has to be 0. So, it is that bilinear function f of zeta eta, which would be 0. Is the process clear now? How to find the shape functions? Any doubts? Any questions? Given any element in that case, actually speaking, whether you have 4 nodes or more nodes, quadrilateral shape or triangular shape or whatever it is, you should be able to use this logic. What was the logic? N1 should be equal to 1 at node 1 when I substitute the coordinates of node 1. It should be equal to 0 at all other nodes. Here there are 4 nodes, so I wrote 2, 3, 4. But it should be 0 at all other nodes, however many nodes are there in the element. So, I can use that logic to build more and more complex elements and their shape functions. So, the challenge that I have told, process of finding shape functions, etc., that is now resolved using natural coordinates. Is that clear? Okay. Now, let me see if that is a next challenge I am going to take, modeling geometry in 2D things. Let us see if that is what comes up. Is the process clear? Any doubts? Please feel free to tell me. Once I have found N1, N2, N3, N4, it is valid for any 4 node quadrilateral element, whether I use it for heat transfer problem, fluid flow problem, structural mechanics problem, or computational electromagnetics, or whatever. It is valid for all these problems. Those shape functions can be used for interpolation of coordinates x, y, or temperature T, or displacements u, v, whatever. It is written as N1 u1, N2 u2, N3 u3, N4 u4. But because in 2 dimensions, it will have 2 displacements u1 and v1, uv, we write it in a compact form, matrix wise. uv at any point p inside the element here is interpolated in terms of nodal displacements using these shape functions. So, in future when I am going to write, while you would complain that before mid semester we were able to work out, things were clearer, after mid semester you have progressed fast, we did not work out anything by hand and all that. I am going to simply write from now onwards delta, meaning the number of variables for that problem. Okay. It could be temperatures, it could be displacements, it could be velocities, whatever. So, and the superscript E means for that element nodes, it is a vector. This is at any point P within the element. These are given by some shape functions N1, N2, N3, N4, whatever. You can put them in a matrix form like this. So, instead of writing out the whole thing, I will just want you to begin to feel comfortable with this matrix notation. It is very easy, compact way of writing it out. That is all. But the problem is, I want to find, say for example, heat flux or strain or whatever. I need the derivatives with respect to x and y, not with respect to zeta eta, right. So, epsilon x, epsilon y, gamma xy, the strains in a two-dimensional structural mechanics problem. Similarly, dou t by dou x, dou t by dou y you can think of. There is no third component, okay, in heat transfer problem. Okay, so these are given in terms of derivatives of the field variables with respect to x and y coordinates. How it comes is a question of solid mechanics. We will not go into that. We start with this and take it forward, how to do the calculations. If you have any doubt how this equation came, you should go back to your solid mechanics notes. Okay. We will not spend time on that. But point is, u, v are given in terms of these shape functions n1, n2, n3, n4. They are given in terms of zeta eta. So, we have to keep switching between xy coordinates, zeta eta coordinates. Okay. So, that is what I am going to do. So, if any function f is given in terms of xy, but x is given in terms of zeta eta and y is given in terms of zeta eta, you want the derivatives. So, you would have written this chain rule, dou f by dou x, and similarly dou f by dou y, correct? Anybody who is not familiar with chain rule of differentiation? No one, right? All of you are comfortable with that. But I would want you to actually write it other way around and write it like this, dou f by dou zeta. Why it becomes evident shortly, and dou f by dou eta. Or in other words, I want you to write it like this actually. Dou by dou zeta, dou by dou eta. The derivatives in zeta eta coordinate frame on the left hand side is equal to the derivatives in xy coordinate on the right hand side with some multiplication matrix, which we call as the Jacobian, which relates these two derivatives. How will the Jacobian look like? It would look like this. If you see this chain rule of differentiation, I will leave it projected for a second for you to see the connection. It is dou x by dou zeta, dou y by dou zeta, dou x by dou eta, dou y by dou eta. Are you convinced? The chain rule of differentiation formula, which we write it out expanded, I have put it in a matrix notation, 2 by 2 matrix. Irrespective of any element that I am going to discuss from now onwards, because I am relating xy coordinates, two coordinates, it is a two-dimensional problem, to zeta eta, this Jacobian will always remain this 2 by 2 matrix, and does not matter whether your problem is heat transfer or fluid mechanics or structural mechanics or whatever, it does not matter. For this coordinate transformation, xy to zeta eta, two coordinates xy, two coordinates zeta eta, therefore it is a 2 by 2 matrix. But what is dou x by dou zeta? One element if you focus on, x is a function of zeta and eta. So, there is a detailed calculation there. X is given in terms of nodal coordinates x1, x2, x3, x4 through the shape functions. Y is given in terms of nodal coordinates y1, y2, y3, y4 through the shape functions. So, the shape functions I have to differentiate with respect to zeta and eta, which is what I have done for a quad 4 element, 4 noded quadrilateral element that we just now discussed. Okay. Because it was n1 was 1 minus zeta into 1 minus eta. If you differentiate with respect to zeta, what remains is 1 minus eta by 4. Okay. Fine. So, I have just done that derivation and given you the 2 by 2 matrix. Is this making sense, or it's a little over the head? Clear? Anybody who has doubt, please ask me. Right? So, what would the Jacobian depend on? this coordinate transformation between x, y and zeta, eta, what would it depend upon? It depends on the shape functions n, because their derivative is what is there in that 2 by 2 matrix. It depends on the nodal coordinates x1, x2, x3, x4, y1, y2, y3, y4. Once you have defined 4 nodes, the shape functions are fixed. We have just now derived them. So, what is really, once you have defined that it is a 4 node quadrilateral element, when you are actually solving a problem, what varies from one solution to another solution will be only the coordinates of the nodes. If all of you solve using the same 4 node quadrilateral element, a given problem, 2-dimensional heat transfer or 2-dimensional structural mechanics, problem domain is given to you. So, when you mesh, you might mesh differently, he may mesh differently, and therefore, x1, y1, x2, y2, x3, y3, x4, y4 may be different. So, the Jacobians will be different. From one element to another element, from one student mesh to another student's mesh. Okay. Does it matter? Is the question. Okay. So, if I am spending so much time highlighting this point, it probably matters, right? So, let us figure out what it matters and why. So, if you go back to this expression, the derivatives in zeta eta coordinates are given in terms of Jacobian multiplied by derivatives in xy. But what I am interested in, for example, the heat flux dou T by dou x, dou T by dou y, or the strains epsilon x, epsilon y, gamma x, y. They are in terms of x and y derivatives. So, I need to flip this equation. Okay, I need to flip this equation. So, which is what exactly I will do now. So, dou by dou x, dou by dou y is inverse Jacobian times dou by dou zeta, dou by dou. And what is inverse Jacobian? For a 2 by 2 matrix, you know, very easy to write 1 by determinant of Jacobian and flip the diagonal elements ko flip karo and other non-diagonal elements minus karo. That is its inverse, right? So, what I notice is that determinant of Jacobian appears in the denominator. So, if you have chosen x1, y1, x2, y2, x3, y3, x4, y4 in such a way that the Jacobian is somewhat distorted, the element shape is distorted, determinant of Jacobian could become a nuisance factor. Okay. So, when you look at a mesh, when you do your course projects using some software, and if some of you are interested in developing a finite element software of your own, okay, when you write a code and you mesh, okay, then you are getting for each node x1, for each element x1, y1, x2, y2, x3, y3, x4, y4, depending on how you have generated the mesh. How good that mesh is will depend on whether anywhere the element is such a way that it is somewhat distorted and Jacobian is likely to pose a problem. So, how you sense this? You would look at it from the point of view of included angles at element vertices. When you look at x1, y1, x2, y2, x3, y3, x4, y4, the shape of this element in the actual physical xy coordinates, not the parent element. Parent element is always perfect square. So, that does not matter. How you have transformed it to the real physical xy coordinate element, that is what is this Jacobian telling you, coordinate transformation. So, how did you stretch it, how did you compress it, how did you rotate it? If you have distorted it badly, the included angles became very bad. They were originally 90 degrees. In the process of making it a quadrilateral element in the real physical xy coordinates, if you have stretched it, squeezed it, rotated it badly, then the Jacobian will be formed. So, when you do this in any software, after meshing, before you go for solution, because you are going to do these course projects now, probably some of you already have attempted to get some preliminary solutions and so on. So, when you create a mesh, before even solving, the software package usually gives you warnings. Okay, look here, in this region, the elements seem to me to be distorted. Do something about it. Okay. If you are not going to look at that warning, then your results are likely to be poor in those regions. Okay. If you don't want to intelligently do anything yourself, you can permit the software itself to do it on its own. So, then it would do remeshing in those regions where the included angles and aspect ratio of the element, okay, one edge is very small compared to other edge, like this, it has a set of measures. It will try to remesh the whole region of that sub-region where there is problem to make sure that the Jacobian is proper. Before it can actually, it needs to actually solve the problem. Based on the meshing itself, it can tell you warnings, how the solution is likely to behave. Because long back at the beginning of the course, we were discussing the case, I am thinking of finite element solution, approximate solution, because I don't know the exact solution. So, when I am doing it using a software for a real world problem like an automobile or an aircraft or a building or ship or something, I don't know the exact solution. How will I find out my approximate solution is going to be good or not? This is one of the measures. Before actually solving the problem, when you mesh, the quality of a finite element mesh will depend upon how the elements are distorted. Ideally, you would want all the elements to be perfect squares. So, it is just a scaling from the parent -1, 1 coordinate system to real physical world, but geometry will be complicated. So, you can't get everywhere perfect squares. So, the process of distortion, this would be one of the measures. So, the software is intelligent enough nowadays, whether or not we are aware and we do some corrective action, the software can take care of this. The program developed by your seniors from all over the world, employed in companies like ANSYS, Abacus, COMSOL, whatever, MATLAB, okay. There are features in the program which will take care of this feature. So, they have already programmed it, that when a mesh is generated, the program will look for all the elements ka Jacobians, see where it is likely to be distorted, which region. It first gives you warnings. If you have not switched on the option to remesh automatically, if you have switched on the option, then it can do the meshing again by itself, so that you avoid this trap. So, first level of check is that we don't know the exact solution, but errors we can reduce by making sure that the mesh is of high quality. Okay. Now, you must have come across Jacobian in some other context. Anywhere else you have come across Jacobian? I always like these side stories and detours, and then make a connection. Where did you come across Jacobian? Integrations. Okay. Cartesian to polar, okay. Basically one coordinate system to another coordinate system. But why are you interested in that? What was the physical problem? Or in the robotics field, okay. What you want for? Why you want that? Why Jacobian is there? Correct. So, if you are, for example, so he is saying that we can encounter it in robotics. Okay. So, suppose you are thinking in terms of a robot which would come and pick up something and keep it somewhere else, right? So, you have multiple coordinate systems you can visualize. This is in some real world physical space. This, it could be a conveyor belt, something is moving here, there, lot of work machines are there. So, you are picking up something, some action is happening here, then it is going to some other action center, some other work center, something is happening there. So, your real physical world x, y, z coordinate frame. Okay. Then your motion is happening because of various joints. There are motors. Each motor has its own coordinate frame, therefore. What is the current you would give, supply voltage and current is what you would control to get whatever you want about the speed and the torque, depending on the motor characteristics, right. So, the joint coordinate frame, you need to get what is the input I need to give to the motor to get some velocity. So, first this is the belt, conveyor belt is moving like this. So, I need to get the tip, the gripper end effector of the robot should approach this particular point in the capital XYZ coordinate frame, global XYZ coordinate frame with a particular velocity in that direction. Then only I will be able to pick up that object, only when these two velocities match, right. And I am going to pick it up with a certain force, and that object, for all you know, could be a metallic object, workpiece, or it could be even a rasgulla or an electric bulb, right. So, you need to hold it, not just approach that particular point with a particular velocity, but you should hold it, grip it with a particular force. Otherwise, that rasgulla will get squeezed out, nobody would buy your product, the electric bulb would shatter, right. So, in each case, you should be able to control the position, velocity, force at this point in the XYZ coordinate frame, vis-a-vis the motor only knows its own coordinate frame, it does not know what happens, right. Vis-a-vis what you get at the joints, which you would regulate through your control algorithm, how much voltage current I am supplying to that motor. So, continuously you will be doing this coordinate to coordinate transformation in robotics, and you would have therefore come across determinant of Jacobian related issues, singularity positions, fully तुम्हारा आपका arm fully stretched out हो गया, then you are in trouble. Your dexterity will be affected, how you can flexibly move. If you would be able to move in a certain region, if your arms are fully stretched out, then you would not be able to execute the tasks. So, you would have concerned about Jacobian reflecting certain difficulties faced in that problem domain. So, you would, when you come down one level or layer below from the real physical world problem, this Jacobian in robotics and angles, etc., maybe something, finite element analysis, ANSYS, Abacus, COMSOL kind of software environment, solving computational fluid dynamics or heat transfer or structural mechanics problems, Jacobian, it looks very, very different problems. But when you come one layer below and look at what is happening inside, then you would be able to see the connections, underlying connections. Then you would be able to appreciate immediately this concept to that concept and so on and so forth, connections you will be able to make. Now, the other challenge we have posed, so I will come to that and I want you to think it over before the next class. Now, so far I have discussed only a 4-noded quadrilateral. So, xy to zeta eta mapping, that is linear. So, one straight edge I have been able to transform to a straight edge in the real physical xy plane. Supposing I am trying to model a circular hole, okay. In the real physical world, it's possible, right? Circular geometry is very commonly used. So, if I want to get a circular curve, arc, okay, your structure could be here, domain of interest could be here, this could be a hole or vice versa, whatever you want. I have just taken one example. So, I have shown how I am modeling it with say 3 elements, but each element is a straight edged element now. So, I put 4 nodes on that arc of a circle 0 to 90 degrees. I want to get that circular arc, but I have put only 4 nodal points. Between the 4 nodal points, I will have straight edges and I build the quadrilateral element. This does not matter to our discussion right now. Focus is on this. So, along this edge now, so what I have achieved, the blue is the actual circular geometry. Okay. So, in all these elements, I have added material which did not exist. If it was a circular hole that I am trying to model, then I have added extra material, right. So, what do I do now? How do I reduce this error? Refine the mesh. Refine the mesh. So, you have 2 options, H refinement and P refinement. So, I can, instead of 3, I can take 300,000 elements. So, each will be a chota sa straight line like that. So, the extra material I have added will become less and less, but can never be 0. You understand my point? So, discretization error of your inability to model a circular hole exactly will never go away. This is an additional new error. It has come because you have to model a curved geometry with a straight edged element. This was not a problem in one-dimensional analysis. It has come up only in 2 dimensions and it would also be there in 3 dimensions now. You can easily imagine that. Okay. So, one route I have is that I can choose more and more elements to model that arc, that fillet radius, okay, and then I will be representing it more accurately. But you would have to think whether or not this is an important geometric feature that you need to model. Now, imagine, for example, okay, those of you who have taken a course project related to biomechanics, let us say. Okay. Now, biomechanics, let us say you are thinking in terms of, say, the knee joint, which is one of the most worked joints in the body. I understand that is most of your body weight would go on to the knee joint. You are trying to model, say, supposing some group has taken that as a course project. Now, how do you model the knee joint? You may have some X-ray or CT scan or some image from sources that you are converting it into a CAD drawing. Now, that you are modeling using FEM software to mesh using elements, 2-dimensional or 3-dimensional or whatever. Then comes the question, there will be so many features in that real physical knee joint. If you start modeling every single feature with hundreds of thousands of elements so that you do not want to miss that geometric feature, then your problem will become intractable almost. So many elements that you will need, you will never be able to submit your course project. So, when you are attempting finite element analysis for real world problems, like for example, this room ka ceiling you want to model, see how many features are there in this. you have to take an intelligent judgmental call. Okay? Are all those geometric features important to model or not? Are they going to be in critical regions? Will failure happen there? Will critical buildup of temperature happen there? This is a question that your judgment of the course comes from the course's knowledge you have gained in solid mechanics, heat transfer, fluid mechanics, electromechanics, whatever domain. So it is domain knowledge that you should have, which will help you to decide यहाँ पे कितना elements लेना है. So when you submit your course projects, just because you have a good computational resource, you beat it to death with hundreds of thousands of elements, we are going to beat you down with poor marks. We want you to be intelligent in using the software, not blind users of software, but intelligently apply it depending on the problem domain, physics of the problem. Try out different meshes. Nobody knows it beforehand if you are solving a new problem. So you will try out with increasing complexity and return on investment kya hai? Are the results changing significantly or not? So this is about H refinement. I want you to think, and I would leave you there. Can we get nonlinear transformation? This edge in the natural coordinates will always be perfect square, right? That we don't want to change. From that, through some nonlinear transformation, P refinement, we always had two routes, right? H refinement, P refinement. So through P refinement, can I do some nonlinear transformation of a straight edge in zeta eta coordinates to a curved edge in the real physical xy plane? This is where actually the Jacobian and the distortion and all that will kick in even more prominently. When I am now trying to straight edge to straight edge, itna kharab nahi hoga. It's easy to visualize, but when you think in terms of now distorting it to model curved geometric features, a wonderful car exterior shape you have designed. Your friends in IDC have designed a beautiful shape of the racing car that you are trying to design. And now you want to see how is the drag when it goes at a very high speed, how is the drag? Okay. So that polynomial curve that he has designed, you want to get in here through this coordinate transformation. What could be the nonlinear transformation? What are the challenges? What are the issues? What is the curves that I can get? What I can't get? How much will be the discretization error? You think about it. We will just introduce you to this in the next class when I talk about higher order elements, but details you have to figure out. Okay. Thank you.